everyone, welcome back to Global Education Zone, and this is the physics channel. And today we're talking about a very important topic in physics, which is called waves. Now, wave is very important. Wave is like a nutshell in physics. Even today, the light we see, the light that comes from this camera to show me, to show this board, to show everything you see, those are light waves. The waves that carry my speech from my mouth to you, to the camera, to the microphone of this phone, is also a longitudinal waves. That's a type of waves. So wave is everywhere. Waves are everywhere. Waves enable us to see. Waves enable us to hear. Waves enable us to use different appliances in our home. That's why I said wave is very important. Now, today we're talking about what waves are. We're talking about what waves are. We're talking about properties of waves. We're also talking about wave equation. We're talking about calculations in waves. So we're talking about this and much more in this video, so stick around and make sure you gain something. So first of all, waves. What are waves? Now, a wave in simple terms is basically a disturbance that travels through a medium. And that medium could be air, that medium could be water, that medium could be anything, any material. So a wave travels through a medium, and that medium could be nothing, because light waves can travel to nothing. And when it is nothing, it's called a vacuum. So waves travel through a medium or no medium, and they transfer their energy from one point in the medium to another without a permanent displacement of the medium. So wave is any disturbance that travels through a medium. It carries energy through the medium, but it does not energize the medium permanently. That means it's just like when I come into when you watch this video now. This video gives you knowledge, right? But it does not give you permanent knowledge. What you learn from this video, you will still forget if you don't revise. So that's what waves do. Waves just pass through a medium, they energize them temporarily, and then the particles are back to their initial state of rest. So a waves, this is general wave motion. So a wave looks like this, and then we have our axis. When you representing in an actual wave. So this is how a wave looks. So a wave motion, what I've just drawn is a wave trajectory. The path of a wave is called a wave motion. Now this is called a wave motion. And this wave motion is the process by which a wave travels through a medium and disturbs the particles temporarily. So that means, now if this is a particle, the particle is disturbed. These are particles, but this is their equilibrium position. So this center line that runs through is for the time of the wave, time taken for the wave to travel. This is the axis of the vertical motion of the particles, and this is the axis for the horizontal motion. Now when the particles are below their equilibrium position, they are in a negative displacement, and when they are above, they are in a positive displacement. So this shaded area here is for positive displacements, and this shaded area here is for negative displacements. So those are the properties of waves. So a wave has positive and negative displacement, but no matter what happens, when this wave moves through this part and goes here, this part eventually returns to its equilibrium position. That's why I said a wave is a temporary disturbance. Not just a disturbance, it's a temporary disturbance which passes through a medium and it energizes it for a moment or a few moments, and then the particles are back to their initial state of rest. Just like temporary energization. Now, we'll talk about this as Y. There are many different terms we can use in waves. We can talk about the amplitude. The amplitude of a wave is the maximum crest. Now, a crest is basically a point on the wave, the top of the wave. That's what is called the crest. Now the maximum crest is called the amplitude. That's the maximum displacement of the wave from the equilibrium position. It's called amplitude. So amplitude is the maximum displacement of the wave. Then we have crest. Crest is a top. It's the top of the positive displacement. So the crest is the top of the positive displacement. So note here that there is a difference between your crest and your amplitude. Your crest is just the top of your positive displacement. So this is a crest, and if I parameter draw another one here, because some waves are compound waves. So in subsequent video we'll talk about different types of waves. Some waves don't have equal positive displacement. Some can have minor and some can have medium. So the top of this one is also the crest, though it is not the amplitude, but it's the highest crest that's called the amplitude. So that's a difference I want you to note. So amplitude is the maximum displacement of the wave, while crest is the top of the positive displacement. Crest is just the top, while amplitude is the maximum top. You understand that? Now your throw is the bottom of the negative displacement. Throw is the bottom of negative displacements. So now I've just outlined the three major terminologies used in waves. Now we'll talk about the next one. We'll talk about is the velocity, the frequency, the period, and the wavelength of a wave. So let's talk about that now. So the velocity of anything is basically the rate at which it's moving, right? So now the velocity of a wave, which we'll talk about now, is the rate at which the wave is moving with time. And that velocity of a wave is measured in meter per second. That is the unit of wave's velocity. So I'll set an equation up now. And that equation is the general equation of a wave. And this equation is very important because wherever you go, you will still make use of it. Even no matter waves, wherever waves you are talking about, universally, this equation V is equal to F lambda is used. Now this equation, how did they get this equation? This equation states that the velocity of a wave is equal to the frequency, the product of the frequency, and the wavelength. In a subsequent video, we'll be talking about calculations in detail in this equation, but we'll also talk about calculations today, but not in detail. So now this equation is called the wave equation. This is the first wave equation. Then we have another wave equation, which is y is equal to a sine 2 pi x over lambda. Now this is called the phase difference, and this is kind of like the phase angle. Now in this 2 pi x over lambda, these are the two principal equations you use in your wave. This is equation 1, this is equation 2. So for most calculations you'll be doing in your wave, you're making use of these equations. Now these equations, we can even simplify these equations. Let's see. We can simplify these equations in different ways. Yes. Now, if there's a displacement, that's if this is when it's in equilibrium position. But now, if there's a displacement, your wave equation becomes y is equal to 2 pi over lambda, the open bracket x minus vt. So that vt, that x is the distance, right? Now that's vt. When you multiply v velocity times time will give you distance, because velocity is what? Distance over time. So your distance or displacement will be equal to what? D is equal to Vt. So your displacement is basically your displacement. This y is your vertical position. That's a sine 2 pi x. This x over lambda minus 2 pi. Then your displacement is Vt, 2 pi Vt. Now, you still put your over lambda. Now, let's convert this equation into forms we can make use of. Let's factorize the 2 pi over lambda. That's a sine 2 pi over lambda. The open bracket x minus Vt. So this is another form. This is another form you can express this equation. Another form you can express this equation is that you can express in terms of frequency. Now we said v is equal to f lambda, right? You can say this is y is equal to a sine 2 pi x over lambda minus 2 pi. V is what? V is f lambda. 2 pi f lambda t for lambda. So lambda will cancel lambda here. We have is equal to a sine 2 pi x over lambda minus 2 pi ft. Now this stage we've got to in this equation is a very important part of this equation, because we can use it to understand different parts of the equation. Now we can also express the equation in terms of the angular velocity, angular speed, angular velocity. So w is equal to f is equal to w over 2 pi, right? So you can say f is equal to w over 2 pi, right? So we can now substitute w over 2 pi here. We can say, so y will be equal to what? A sine 2 pi x over lambda minus f is what? 2 pi minus 2 pi w over 2 pi, then the t. So we've converted f is equal to w over 2 pi. We've substituted into this equation. So 2 pi will cancel 2 pi here. We have y is equal to a sine 2 pi x over lambda minus what? What do we have here? Minus wt. So with different substitutions, we can convert this equation into the form we want to use. So this is the final equation we get. This is the final equation because this equation is manipulatable. We can easily manipulate this equation. So the next part of this class, we're talking about the properties of waves. And there are 5 major properties of wave. They are reflection, refraction, diffraction, interference, and polarization. Now, reflection here is just like when light casts upon this smooth surface, you see a reflection of yourself. When you check your face in the mirror, right, your rays return back to you. So when those rays of light return back to you, it's called a reflection. Reflection, when you look at the surface of a pool of water and you see yourself back in your eyes, that's a reflection. So waves are like balls. When you throw a ball at the ball comes back to you, right? So that's a reflection. A reflection is basically when a wave hits a hard surface and comes back. But when it comes back, it does not come back in the same direction. It comes back in a different direction. So that means when you reflect, when a wave hits a surface, assume this is a pool of water. When a wave hits a surface, waves from the sun, it always comes out in a different direction. So more about that in a later video, but this angle is called the angle of incidence, and this angle is angle of reflection. Sorry, I made a mistake. This angle here is the angle of incidence. The angle between the incidence ray and the normal, and the angle, this angle here is called the angle of reflection. So that is, these are two angles formed when waves hit a surface and reflect. Then we have smooth reflection and diffuse reflection. Whenever there's smooth reflection, you can be able to see your face directly. But if there's diffuse reflection, like as in here, I can't see my face directly on this board. Even though this board is a little bit transparent, I cannot see my face because this surface is not very smooth. But in an extremely smooth surface, you tend to have smooth reflection. And those extremely smooth surfaces, they are surfaces like the surface of a mirror. When you have plain glass, silvered glass surface, that surface becomes very, very smooth, and light hits at an incident angle and exits at a proper refraction angle. You understand? So now we'll talk about refraction. Refraction is basically the fact that when light hits a surface, it not only bounces back, but an amount of that light will also pass through. So when that light passes through that surface, it's called refraction. And that refraction, it also changes direction, because when light hits a pool of water, it enters the water. Some of it is reflected and some of it is refracted. So those that are refracted are the ones that pass through the water. So it's represented like something like this. You still have some rays that still come down, but this angle of incidence, this is called the angle of, if this is normal, this angle of refraction is also R. Let's carry it as capital letter R. So this angle of refraction here, it is the angle with which the ray enters the water, and that angle is always different from the angle of incidence in most cases. But the only way it will be the same is if these mediums are the same. Now I'm assuming this is water. If this is water and this is air, if it's water and this is air, so some rays of light will hit the water and be reflected. Some rays of light will hit water and be refracted inside. So that is this difference between reflection and refraction. So reflection is basically when a ray hits a surface, reflection, and it bounces back in an opposite direction. It changes direction and it changes some part of its properties. Kind of like the velocity and direction are changed. Then if in refraction, the direction of the wave is changed and the velocity is also changed. That's one property of refraction. And also, in addition, the wavelength also changes when it hits such properties, when it hits such surfaces. Because sometimes if the wave is coming with a big wavelength, and wavelength is basically, I'll talk about wavelength soon. Wavelength is basically the distance that the time taken for the wave, or rather the distance covered by the wave in one complete revolution. So, but period is the time taken for the wave to cover one revolution, but wavelength is the distance covered by the wave in one revolution, and one revolution is like one circle. Just like when you go around the circle once, that's what wavelength is. I forgot to explain that when I was explaining the principal properties, but I'm explaining it now. A wavelength is the distance covered by a wave in one cycle or one oscillation. So when it goes up and it goes down, and when it's coming back up, that is one wavelength. I will demonstrate that when I'm trying to do the questions. Then we'll talk about the diffraction. Diffraction is when a wave passes through a tiny opening. So like when you have a very tiny pinhole and light comes out from the pinhole. Like the camera, I'm making a video now with my phone, and the camera of my phone is like a pinhole. So light rays are coming outward from the camera. Light rays are coming into the pinhole of the camera. So that is diffraction. The light is being diffracted, and in diffraction there's some amount of bending in the light rays. Diffraction does not mean the light just goes straight. When the light bends, the light comes from a wide angle and then bend into the thin angle of this camera by which you are watching me and you are hearing me. So now that is diffraction, when waves travel into thin openings. Then we'll talk about interference. Interference is all about when a wave is disrupted by another wave. And in interference, if that disruption is in the right angle, it will enhance. But if that interference is in the wrong angle, they will be scattered or they will be nullified. So, and when those waves are nullified, it's called a stationary wave. When two waves interfere in opposite direction and cancel each other, it's called a stationary wave. Let me explain myself. Imagine you are running and you hit another person. If you and that person are running from opposite direction and you hit, two of you will not go anywhere. You will just hit and fall down. That's if you are going with the same force. But imagine you are going with the same direction. You are running the same direction. So when that person hits you, it's like pushing you forward. So you move faster with more momentum. So we'll talk about momentum in the subsequent video, but that demonstrates destructive and constructive interference. So when the interference makes the waves move faster and with more power, it's called the constructive interference. And when the interference makes the wave move with a lesser power or cancel them out, it's called a destructive interference. And a very good example of a destructive interference is stationary waves. Stationary waves are the waves formed by musical instruments. So when those musical instruments, when you blow them, the waves go in and out. So and those waves cancel each other, and that's why we can hear sound. So stationary waves are not just useless. Destructive interference causes stationary waves, and those stationary waves are useful in our musical instruments, useful in sound. When you hear somebody speaking from a speaker, any instrument, they make use of destructive interference, stationary waves. Constructive interference are used when you put a speaker in an open room. When the wave reflects back in resonance, that resonance makes the wave look louder, right? When you put your phone on the table and the table rattles, the table shakes. So constructive interference is the cause of resonance, and destructive interference is the cause of stationary waves, and as a result, our musical instruments sound. So that is mostly our interference. Interference is a very wide topic which I want to talk about in detail in another video, but today we'll just talk about the waves as general. Then next we'll talk about polarization. Polarization is about the fact that waves can actually move in different planes, and polarization occurs only in transverse waves. So transverse waves move in different planes. What that means is that when there's panic somewhere and people run in different directions, right? Now, out of those people running in different directions, if there's a door, only the person running straight can enter that door, right? Those people running in different directions will be scattered, right? So, and even if you have a ball now, like when you are playing, there's a sport called bowling, right? Now in bowling, when you pick your bowling pin, when it rolls and enters into when it hits what is supposed to be the target, when it hits the target and they enter inside, it's kind of constructive, you understand? And that is just the way polarization works. When the waves hit straight, they hit in the right direction, they are going to enter, they are going to pass through the medium. But when they are not indirectly, they are going to divert, they are going to be cancelled out. So and polarization is used when we make use of sunglasses, just like my glasses. There are some sunglasses that they are used to reduce the intensity of the sun. They are called anti-glare sunglasses. So those sunglasses, they are going to select those waves that are coming in the right direction, and they are going to reject the ones that are not coming in the right direction. That's how the phenomenon of polarization works. So and polarization can only work in transverse waves. So that being said and done, I want us to move into calculations and demonstration of wave equations. So now calculations. Let's talk about calculations. I will do a couple of calculations in waves to illustrate what I've been saying so far. To illustrate what I've been saying so far. Now, the first calculation, we'll talk about a radio station. A radio station broadcasts as a frequency of 600 kilohertz. Now, the unit of frequency is in hertz. So, the frequency of the wave is 600 kilohertz. Now, they said if the speed of light in air is 3 times 10 per 8 meters per second, calculate the wavelength of the radio wave. Now, the speed of light, that's V, is what? 3 times 10 per 8 meters per second. That's automatically also the speed of light. So most natural waves propagate at the speed of light. Now they ask us to calculate the wavelength of the wave. Now we'll go back to our formula. V is equal to what? F lambda. Now we have F and we have V. We are looking for what? Lambda. Now let's dividing both sides by F. We have F cancel F. So V over F is equal to lambda. Now V is what? 3 times 10 to the power 8 10 to 8 the power of 8 over F is what? 600 kilohertz. Now we have to convert 600 kilohertz into the standard unit, and that is hertz. Kilo is times 10 raised power 3, right? That's 600 times 10 raised power 3. So when we cancel this is 10 raised power 5. It gives us 5 because that's divisive power of index. So 10 raised power 8 minus 10 divided by 10 raised power 3 is 10 raised power 5. That's 10 raised power 5. So we are left with 3 times 10 raised power 5 over. Now you can see it reduces that. This is 6 times 10 raised power 2. We'll still reduce this as 10 raised power 3. Then we have 3 times 10 raised power 3 over 6. So 3 divided by 6 is 0. 3 in 3 1, 3 in 6 2. That's 0.5 times 10 raised power 3. And that's also what? 5 times 10 raised power 2. And what's our unit? Our unit is, we're looking for what? Lambda, right? Our unit is in meter, standard unit, because we have already done the conversion before we calculated. So the wavelength of the wave, of the radio wave, is 5 times 10 raised to meter. So question 2. Which of the following is not the property of longitudinal waves? A. Compression. B. Reflection. C. Refraction. D. Polarization. E. Diffraction. Now, which of these are not the properties, is not a property of longitudinal wave? Now, they said number A, compression. Compression, I didn't list it among the 5 properties of wave. The 5 properties of wave are reflection, refraction, diffraction, interference, and polarization. There's nothing like compression. So number A is the right answer. Compression is not a property of longitudinal wave. Number B, reflection. Yes, reflection is the property of longitudinal waves. Refraction is the property of longitudinal waves. Reflection and refraction are properties of all waves, not just longitudinal waves. Then polarization is not a property of longitudinal waves. So A and D are the correct answer. So basically, it asks us to pick the ones that are not properties of longitudinal waves. Then option E, diffraction. Diffraction is a property of longitudinal waves. So only compression and polarization are not properties of longitudinal wave. Then lastly, we'll talk about another calculation. Number 7, a wave sent out from its source is reflected back to the source in 1 times 10 raised power 3 minus 3 seconds. So now we have a wave. This wave is sent to the source and then it comes back to the source. In the time taken is what? Is 1 times 10 raised power minus 3 seconds. 1 times 10 raised power minus 3 seconds. Now they said if the velocity of the wave is 3 times 10 raised power 8, so the v is what? 3 times 10 raised power 8 meter per second. Then I said the distance of the reflecting surface from the source is what? The distance of the reflecting surface from the source. Now, the asking us to calculate this, so let's call this D. This should be D. The distance of the reflecting surface from the source. Now, what's the total distance traveled by the wave? The wave travels like this and travels back away, so it has travels D plus D. So total distance is what? Distance traveled is what? Is D plus D. Now it's 2D. Now the total time taken is what? Is 1 times 10 raised power minus 3 seconds. So now the velocity of the wave is 3 times 10 raised power 8 meter per second. Now they said calculate what? The distance of the reflecting surface from the source. Now we want to use a formula called this V is equal to F lambda. This time taken, a wave sent out from the source is reflected back to the source in 1 times 10 raised power 3 seconds. Okay, if the velocity of the wave is 3 times 10 raised power per second, the distance of the wave from the reflecting source is okay. Good. Now you know that distance is equal to distance. V is equal to distance over time, right? So we have something like this. The velocity is equal to what? Distance over time. So this time around we are not using v V is equal to epsilon. Now we are using V is equal to d over t. Now I said the distance of the source. Now what does it travel? The distance travel is what? 2d. So the velocity is what? So distance is what? V times t, are we? Distance is V times t. But instead of d, we are using 2d. Why? Because it has traveled twice the distance. So 2d is equal to V over t. Is equal to Vt, sorry. So d is what? Divide 2 by 2. Divide both sides by 2. So d is what? This is Vt over 2. So V is what? 3. 3 times 10 power 8 times t is what? 1 times 10 power minus 3 over 2. So let's do some pressing of calculator buttons. Let's see what that gives us. What that gives us? 3 times 10 power 8. 3 8 times 1 plus 3. Very good. So our answer is 150,000. So our answer is what? 150,000. So expressing this around that 1, 2, 3, 4, 5. That's 1.5 times 10 to the power 5 volts. What's our unit? We are looking for distance, right? Our unit is meter. So that's said and done. That is the solution of. So the option is option D, 1.5 times 10 to the power 5. So we got it right. So today we'll talk about waves, talk about properties of wave, reflection, refraction, diffraction, interference, and polarization. We'll talk about a general overview of waves, how we can see waves, how waves are a part of our lives, how light waves travel, how waves we see and hear with waves, and how waves are everywhere. We'll also talk about some calculations in waves, talk about properties of waves, which I mentioned earlier. In the subsequent video, I will go in more detail on waves. We'll talk about light waves and sound waves in much more detail. So thank you for watching and good luck.